Hi folks, welcome to the 3.8 video where we're going to talk about inverses and radical functions. So I want to start today with a little bit of what we know. And what we know is, turns out we know a lot about inverse functions, right? So we think about maybe addition, right? So let's say we wanted to have where we're adding 5 to something. How would we undo that? And I think we know that if we have addition, we add 5 and we wanted to get rid of that 5, we would subtract that 5, right? So addition and subtraction, they undo each other. So we call them inverse functions. Now, what other pairs of operations do that? Well, we could have multiplication. And how do we undo that? We undo it with division. Let's think maybe fast forward a little bit in our math careers. Along the way, at some point, we learned how to square a number. And if we wanted to get rid of that square, we had a square root. And as we moved further along, maybe we learned that we could cube something. And if we wanted to undo a cube, we would have the square root symbol, but there would be a little 3 out there instead. Right? So that's a cube root. And then one pair that we learned in the last chapter, chapter 4, was we actually learned that if we have a natural exponential function, so e to the x, we could undo that by saying natural log, right? And so all of these here are examples of what we can say are inverse. So addition and subtraction, multiplication and division, square and square root, cube and cube root, and e to the x and natural log. And so let's take a look at what's new today. Well, we're going to talk about general strategies, right? In particular, we want to talk about different strategies on how we can actually find these inverse functions. That might be, how do we find them with numbers? That's an important way to know how to do that. Finding it on a graph, that's another important way to find inverse functions. And then lastly, we're going to take a look at how we find inverse functions algebraically. So that's where we are headed today. Now, before we get too far, let's make sure we have a really good working definition of what we mean by an inverse function, right? We also want to be really thoughtful about not just the definition, but the notation, right? How do we write it in a math way so that we know what it means when we read it, but also other people know what we mean when we write it? So let's take a look at this definition. Inverse functions allow us to undo other functions, right? So this idea of a square and a square root, or adding and subtracting, these functions undo each other. Now, in general, we're going to use the following notation to describe functions and inverse functions. And so we know that if we have a function, maybe we write it as f of x, this is what we're going to refer to as the original function. So f of x typically refers to the original function. However, if we want to say inverse function, we're going to have f with a little superscript of a -1 of x. And when we see that -1, right, so let's go ahead and highlight that. When we see that -1, that's going to think for us, we're looking at an inverse function. Okay. Now here's the tricky part, right? We have f of x as our original function, f -1 of x is the inverse function. And that's going to be something that we see a lot when we get to Math 104 in a few weeks. But this -1 symbol, we use it in a lot of different ways in math. And so we really need to be really careful that this -1 means inverse, okay? So in this lesson, it's going to mean inverse. But as we move into some other topics, it might mean other things. And so we just have to be really aware of that. Okay. All right, with that being said, let's take a look at finding inverses with numbers or numerically, okay? So let's read through this sentence right here. If AB is a point on f of x, then BA is a point on f minus 1 of x, all right? Now let's read that again, but maybe let's color code a little bit. So if A, comma, B is a point on f of x, meaning AB is a point on the original function, then it turns out that B, comma, A, right? So let's think about what happened there. It looks like the B and A switched spots. B, comma, A is going to be a point on the inverse function. All right. It does turn out that all we do numerically is switch the x and y coordinates, okay? So let's take a look at this first example. If 0, comma 1 is a point on f of x, then something is a point on the inverse function. And it turns out, if we follow this definition over here, if 0, comma 1 is a point on the original function, then 1, comma 0 is a point on the inverse function, right? And we can color code this to match the statement we have above, that 0, comma 1, that's our A, comma B, is a point on the original function. Then 1, comma 0 is going to be a point on the inverse function, right? So all we're doing is taking those x, y coordinates and we're switching them. All right, let's do the same thing for example 2. If 3, comma 9 is a point on f of x, then 9, comma 3 is a point on the inverse function, all right? So fairly straightforward here, but I just want to add a little sentence at the end. So when we come back and maybe review our notes later on, it still makes sense to us, right? And the note that I want us to write for ourselves here is this. You're going to switch the x, comma y to y, comma x to find the corresponding point on the inverse function. All right. So we're going to switch xy to yx to find the corresponding point on the inverse function. All right. Now let's take this idea and let's dive a little bit deeper. Let's think about what it means to find inverse functions graphically. All right. And so let me just sort of zoom in on the page for a moment so you can kind of see where we're going, all right? But what we're going to do is we're going to be taking a look at this function f of x equals x squared, and we're going to graph this function. And then we're going to think about what the inverse function is, and we're going to graph that as well, okay? Now, before we do that, maybe it would be important for us to read this sentence right here. If f of x and f minus 1 of x are what we call inverse functions, then the following thing is true. It turns out that they are symmetric about the line y equals x. And so this line y equals x, we're going to go ahead and color that one green. And we're going to use that when we draw that on the graph, okay? All right, so let's take a look at this first example, example 3. We have f of x equals x squared. Now, I think we all know that x squared is a parabola, and it looks something like this, right? But before we just sort of randomly draw a parabola, we want to be more thoughtful and think about how can we plot some exact points and take the extra 30 seconds to make this a graph that is more accurate, all right? So let's pick some values here. I'm going to pick -3, -2, -1, 0, 1, 2, and 3. I'm going to take each of these and I'm going to go ahead and plug this into the function f of x equals x squared. So when I take -3 and I square it, I'm going to get +9. If I take -2 and square it, I get +4. -1 squared is +1. 0 squared is 0. Now let's look at the positive x values. 1 squared is going to be +1, 2 squared is +4, 3 squared is +9. All right. And we're going to keep using that yellow color. All right, so I'm going to sketch this graph and then I'm going to highlight it in yellow so that we can see what this function looks like. And let's plot those points right here. So I've got 0, 0, 1, 1, 2, 4, 3, 9. I'm going to do the other points on the negative side. -1, 1, -2, 4, -3, 9. Now let's see how good my drawing is today, but we're going to go ahead and connect these. Not too bad. All right, not too bad there. Say that's pretty good for a sketch. All right, so what we have right here, and let's just trace over this in the yellow, is we have our original function, right? Now, let's go ahead and think about what the inverse is, right? So we kind of hinted at this in the beginning. We said if we square something and we want to undo that square, we're going to have to take the square root. And so if we think about the inverse function down here, that f with the -1 of x, we might notice that this is going to be the square root of x, all right? And so let's think about what values we can plug in for x, all right? So if I take the square root of 0, I'm going to get 0. And if I take the square root of 1, I'm going to get 1. What's another nice number to take a square root of? Like square root of 2 is a decimal, that's going to be hard to graph. Square root of 3 is a decimal, that's going to be hard to graph. But square root of 4 is going to give me 2. And if I use that same reasoning, maybe the next quote unquote nice number I should plug in for x is going to be 9. And when I take the square root of 9, I get 3. Right. Now, let's think about what happens over here though, right? What if I gave you -1? And I said, take the square root of that. Well, I'll give us a little hint. This is going to be in section 3.1, but we would actually get the number I. Okay. I stands for imaginary numbers. And I don't want to get too far into that right now, but it's an imaginary number. All right, well, what if we did the square root of -4? Turns out that would be 2i. And if I did the square root of -9, I would get 3i. But you know what, folks? For right now, these, my friends, are imaginary numbers. And so we don't see them, not on the real XY axis. All right, so those 3 points, we actually don't see them. So if we were to graph the square root of x, right, we're going to just graph the real numbers that we see. 0, 0, 1, 1, 4, 2, 9, 3. So let's see what that looks like. 0, 0, 1, 1, 4, 2, 9, 3. I'm going to connect those with a nice smooth curve. And let's color code this in the pink so we know that this is our inverse function, right? Now, the last part to this graph that I want to include here is this y equals x. All right, and so let's do that in the green color. We're going to draw a line y equals x, and I hope that we remember that line is just a diagonal line that kind of cuts through the plane. Okay, so if we graph that, it goes through 0, 0, 5, 5, 10, 10, -5, -5, -10, -10. And here's where the technology is going to help me out a little bit, I hope. If I can sort of get that close enough. Yep, turns it into a straight line for me. All right, so here we have our y equals x. Now, in this definition that we saw earlier, we said that if f of x and f minus 1 of x are inverse functions, then they are symmetric about that line, right? Now, symmetric means that if I take one graph and I sort of fold it over that line, I should get the other graph, right? So I'm just going to leave the red part here for us. And if you could all just turn your head a little bit to the right, I think we can see that the yellow and the pink sort of match up, right? Now, some of us might be saying, all right, now some of you might be wondering, why is it that we only have one part down here in our inverse function, right? And this is actually a super, super important point that I want to drive home here. If we took the whole yellow parabola and we reflected it over this green line, we would, like I drew earlier, end up with this sideways parabola, okay? However, we want to make sure that our inverse function is also a function, right? And so one phrase that might be coming into our heads right now is something called the vertical line test, right? And so if I draw a vertical line through this parabola, it actually crosses at 2 different points. That means that this sideways parabola is not actually a function, okay? Now, since we want our inverse to be a function, we need to make sure that we only reflect the part that will keep the resulting graph also to be a function, okay? So what this means is that when we find the inverse, okay, let's do that. So sometimes the inverse function has a what we call restricted domain and range. Okay. This is so the resulting function still passes the vertical line test. So sometimes the inverse function has a restricted domain and range. The reason for this is so that the resulting function is still a function and passes that vertical line test, okay? And so just as a reminder, let's think about our domain and range here real quick. If we look at the domain of my original function, right? My domain is going to be all real numbers because my parabola goes sideways forever and ever, while the range is the smallest value I can get is 0, and I include 0. So I'm going to use a bracket, comma, it goes all the way up to infinity, but since we never get to infinity, we put a parentheses there, right? So this is the domain and range for my original function, my x squared. Let's see what we can write for our domain and range of the inverse function. So the domain here, we use the picture to help us. Well, the smallest x value is 0, and then I get all the positive values all the way to infinity. So for my domain, I can say bracket 0 to infinity, parentheses, right? And the range, well, let's see. The smallest y value is 0, and I get all the y values above that. So my range is from 0 to infinity. All right. Now, if we color code this in the pink, so we know this is the domain and range that goes with the inverse function, we might notice that the range or the y values of the original became the x values of the inverse. That's the same thing as saying x and y get switched, right? But we might also notice that the domain of the original function is not the same as the range of the inverse function. That is what we mean by sometimes the inverse function has a restricted domain and range, right? Sometimes we need to restrict it so that our resulting graph or equation is still a function, okay? All right, we're going to take a look at one last way of thinking about inverse functions, and that is finding inverse functions algebraically. All right, now I've cut and paste from your textbook here because I think it's important for us to engage in the textbook, right? Sometimes we think, oh, well, somebody else explains it better, so I'm just going to listen to someone else. And the tough thing is, if we don't develop this skill of reading a book, reading a math book, sometimes we can be a little underprepared for courses in the future, right? And I don't want that to happen to us. So I think it's important that we think about how we engage with that text, all right? So here we say, how do we find this inverse function algebraically, right? Given a polynomial function, we find the inverse of the function by restricting the domain in such a way that the new function is something we call one-to-one. Now, one-to-one, my friends, just means that the inverse is also a function. So when someone says that a function is one-to-one, it means that the inverse is also a function, okay? And to do this, we have 3 with a little bit of a hidden step here, okay? So what are our steps? First thing we're gonna do, we're gonna replace f of x with y. Second thing we're gonna do, we're gonna interchange, or we're gonna swap our x and y. And the third thing we're going to do is we're going to solve for y. That's where the bulk of our work is. But I don't want us to forget about this last part here. I'm going to put it as like a separate step 4. We're going to rename the function f with a -1 of x. All right, so we're going to really work on using the proper notation so that we know what it means, but also people who read our work know what we mean. All right, so we've got examples 4, 5, 6, 7, 8. So we've got 5 examples here to look at what we do to find the inverse functions from an equation, okay? All right, let's get started with example 4 here. So example 4, we have f of x equals x squared. So the first step we would write is we would replace f of x with y. So we have y equals x squared. The second step says we're going to switch or interchange our x and y. That would mean we get x equals y squared. Our third step is that we're going to solve for y. So how do I get this y all by itself? Well, I'm going to take the square root of both sides. So I'll get square root of x equals y. And this very last step here, we're going to rename y as f with the -1 of x equals the square root of x. All right. So that's how we follow those 4 steps to find our inverse function. That part's usually not too bad, but we really need to think about this last part, which is let's determine any restrictions on the domain. And so what I mean by that is now that we look at our inverse function, what restrictions do we have on this domain? All right. And so from above, we know that our domain of the square root function is we can only put in a 0, nothing smaller than that, but we can put in 0, and we can put in every single number until infinity. Right? And so there we have fully answered the question. We found our inverse function and we found the domain that has a slight restriction on it. Okay. All right. Let's take a look at example number 5. All right, so example number 5, again, I grabbed this from your textbook because I do think that they have some really good visuals about how to see what we mean when we're finding things algebraically, all right? And so this looks really similar to what we were looking at before with the x squared and the square root of x, that we have this as our line of symmetry. And we can kind of see that this orange graph, if I fold it over, will give us the blue graph, right? And so I'm going to ask you to kind of turn your head slightly to the right now. And you can see that those 2 red curves sort of fold right on top of each other, right? So your textbook gives us this as the inverse function. I just want to make sure we know where this comes from, okay? So let's follow these 4 steps and see. All right. So first thing I'm going to do, I'm going to replace my f of x. Oops. I'm going to replace my f of x with y. So y equals 5x cubed plus 1. All right. Second step, I'm going to switch my x and y. So I'm going to get x equals 5y cubed plus 1. Now, this is where, again, most of the work is. We're going to go ahead and switch our x, not switch, we're going to solve for our new y. Okay, so the first thing I'm going to do is I'm going to take this plus 1, I'm going to subtract it to both sides. So x minus 1 equals 5y cubed. All right, next thing we're going to do, we're going to divide by the 5. So we're going to get x minus 1 over 5 equals y cubed. And last thing to get y by itself, we're going to take the cube root, all right? So the cube root of x minus 1 over 5 equals y. All right, so we found our inverse, but don't forget about using that proper notation, right? Instead of writing y, we're going to replace that with the inverse notation. And so we can say the inverse is this cube root of x minus 1 over 5. Right? So right here, we can see that what we got matches what the textbook has, okay? But I just want to plant a seed here for some really important concepts that we're going to be using a lot when we get to Calc 1 in the spring. So another way that we're going to be writing something like this is going to be x minus 1 over 5. That part stays the same, but instead of writing this cube root, we're going to have it to the power of 1/3. Okay. So again, I don't want to emphasize this too much right now, right? But I want to plant some seeds that for the spring, being able to go back and forth between these 2 versions is going to be super, super helpful. All right. All right. Now we got to figure out the domain of this function, right? We can do this in one of two ways. If we look at the graph, we can tell that all the x values are accounted for, meaning we can put in every single number between negative infinity and infinity to get an output. The second way we can do that is think about what numbers I can or cannot plug in for x. And it turns out I can plug in any number I want for x. And so what that means is our domain is from negative infinity to positive infinity. Or sometimes we write that as all real numbers, which is that fancy script R. All right. Let's go ahead and take a look at example number 6. All right. So sort of similar here. I want us to practice visualizing this, but I also want us to think about the idea of how we do this algebraically. Okay. So let's go ahead and we're going to say this f of x. And if we think about what we learned in the first unit about graph transformations, we should see that this is a parabola. The -2 means we move to the right 2, and the -3 means we move down 3. Okay. That allows us to sketch a graph pretty quickly. So we're going to go to the right 2, down 3. And then we're going to go 1, 1, 2, 4, and then 3, 6. And we could do the same point over here. And we can sketch this parabola. Okay. And so here we have the original function. And I'm going to go ahead and draw in that line of symmetry, right? The x equals y, or y equals x line. And so if we do that, we'll have something like this. Right? Now this one I think is a little harder to visualize. And so what I'm going to do is I'm actually going to write out a few of these points so that it helps me think more easily about what I'm going to flip. Okay. So this point is 2, -3. If I switch my x and y's, I should get -3, 2, or this point right over here. Now, if I find the next point over here, I get 3, -2. And if I switch those, I'll get -2, 3, or that point over there. If we keep going, we're going to get 4, 1, and this point will be 5, 6. And if we switch those, we'll get 1, 4, and then 6, 5. And if I connect those points, I would be able to go ahead and highlight those in the pink. Right? And now this one is going to be a lot harder for us to see visually. Okay, and that's okay. So if you need to sort of pause the video and really think about the visual here, that's absolutely okay. But I find it helpful if we sort of ignore this left-hand side, right? So if I sort of cover that up and we focus on the yellow and the pink that's showing right now, and again, maybe just sort of turn our heads to the right, I think if we ignore the part covered up by the red, we can see that the yellow and the pink are actually reflections of each other. So how do we find this algebraically? Let's go ahead and do that. The neat thing is our answer should totally match up here. All right, so the first thing we're going to do is we're going to go ahead and replace f of x with y. The second thing we're going to do is we're going to go ahead and switch our x and y's. The third step, which is going to require a little bit more work, is we're going to go ahead and solve for our y. So what do we do first? Let's go ahead and add 3 to both sides. So x plus 3 equals y minus 2, that quantity squared. All right, what do we get rid of next? We got to get rid of that square. So we'll get the square root of x plus 3 equals y minus 2. And our last step, we're going to go ahead and add 2 to both sides. We'll get square root of x plus 3 plus 2 is on the outside of the square root equals y. Right? We've got one last step, which is we're going to put it in the proper notation. So we've got the inverse function is going to be the square root of x plus 3 plus 2. Now, I said earlier that our answers should match. And what I mean by that is that the equation for our inverse function, right? The equation for our inverse function should match our graph for the inverse function, right? What we did by switching x and y values. And so let's think about what we know about graph transformation. Well, this is a square root function, so we know it looks something like this. That plus 3 means to the left 3, and that plus 2, since it's outside, is going to mean up 2. That means that this square root function should start at -3, 2. And it does, right? It matches what we have here. So I think that's a pretty neat way to think about inverse functions, that it's not just 3 separate procedures, but really they're just 3 different ways of describing the same thing. Now, before we move on to example 7, let's go ahead and make sure we have our domain here. And so the domain I can see is my x values start at -3 and then go all the way to infinity. Okay. And so let's go ahead and find some space to write that. Our domain here is from including -3 all the way to infinity. Okay. All right. Let's take a look at example number 7 here. Okay, so 7 and 8 are going to be much more similar to each other than the previous examples, but this is definitely going to be some algebra skills that will be helpful once we get to calculus in the spring. Okay, so let's go ahead and apply those 4 steps. We're going to change f of x to equal y. Next, we're going to switch our x and y. So we get x equals y plus 3 over y minus 2. This, my friends, is the tricky part. Now we have to go ahead and find out how we get y all by itself. So we're going to start here by going ahead and cross multiplying, okay? So I'm going to go ahead and take x and I'm going to multiply it by y minus 2. So I'm going to get x times y minus 2 equals y plus 3. Okay. Now this is a really good example of sometimes the questions get messier before they get better. What I mean by that is we're going to go ahead and distribute this x here. So we're going to end up with xy minus 2x equals y plus 3. Now, we're going to look for all the terms that have y, and we're going to put those on one side together. All right, so let's do a little old school, middle school kind of color coding, right? So all the terms that have y are in orange, and then all the terms that don't have y are in this green color. And so I'm going to take this y on the right-hand side. I'm going to go ahead and move it to the left-hand side. And then I'm going to take this negative 2x and I'm going to add it to the right-hand side. And so that'll give me xy minus y equals 2x plus 3, right? So I've got all my green terms on one side and all of my orange terms on the other side. Now, the cool thing about this is all the orange terms have y. That means that I can factor out a y. All right. And so if I factor out a y, I get x minus 1. Now, if I want to get y all by itself, which is my goal, we're going to take x minus 1, we're just going to divide it away, right? Division is the inverse of multiplication. So I will end up with y equals 2x plus 3 over x minus 1. Now we don't want to put a box around this yet because we want to make sure we use the correct notation. So we're going to say the inverse function is 2x plus 3 over x minus 1. Now we need to find our domain restriction. Okay, now for our domain restrictions in these cases, we have to check 2 different locations. The first thing we have to do is say what didn't go into the original function. The second thing we have to consider is what cannot go into the inverse function. Okay. So let's write our domain over here, and we're going to have 2 different lines so that we have one that tells us about our original function restriction and one that tells us about the inverse function restriction. So the number that I cannot put into f of x is the number that makes the denominator 0. So in this case, we can say that x cannot equal 2, and this is from our original function. Right? Because if I take 2 and plug it in here, I'm going to get 0 in the denominator, and we cannot divide by 0. Now, if we use that same reasoning, what's going to be something we cannot put into the inverse? Well, same thing. We need to see what makes the denominator 0. Turns out that's 1. So x cannot equal 1 because the inverse function will be undefined there, right? But when we write this out, we want to use interval notation. So we're going to write it as from negative infinity to 1 in union with 1 to 2 in union with 2 to infinity. And all this says, if we write it out in words, is all real numbers except x equals 1 and x equals 2. All right. So let's talk through this problem one more time before we take a look at example 8. So we change f of x to y. Then we switched all of our x's and y's. And then in step 3, we made things a lot messier before they got better. We cross multiplied, we distributed, and then we collected all the terms with y on one side and everything else on the other. The reason for this is so we could factor out a y and then just divide away the rest of that. Okay. So let's try those steps for example number 8. Step 1, y equals 3x minus 1 over x plus 5. Step 2, switch all of the x's and y's. X equals 3y minus 1 over 3, over y plus 5. All right, here's where things get a little bit messier, but we can do this, right? We're going to cross multiply. We're going to get x times y plus 5 equals 3y minus 1. We're going to make it messier so that it can get better. We get xy plus 5x equals 3y minus 1. Let's see. Xy has a y, 3y has a y. So I'm going to put those on the same side, but then 5x and this minus 1, I'm going to put on the other side, okay, because they don't have y's in it. Now, you can do however you want, like moving things to one side, right? The order doesn't actually matter. I like to keep as many things positive as possible. So I'm going to take this minus 1, I'm going to move it to the left-hand side, which means that I'm going to take this xy and I'm going to move it to the right-hand side. And so when I do that, I get 5x plus 1 equals 3y minus xy. And I do a quick check to make sure all my terms on one side have no y's, and then all my terms on the other side only have y's. Once I've done that, I'm going to go ahead and factor the y out of the right-hand side. So I get 5x plus 1 equals y times 3 minus x. Y is multiplied by 3 minus x, so I'm going to go ahead and divide that to both sides. So I get 5x plus 1 over 3 minus x equals y. Before I box that answer off and say hooray, I'm going to make sure I do this last step. We're going to call it the inverse function equals f of x, or f minus 1 of x equals 5x plus 1 over 3 minus x. Okay. So hopefully this second problem makes this process make a little bit more sense, but I would practice this process a lot because again, it does come up, this idea comes up again in Calc 1, okay? Now, before we finish this off, we got to go ahead and find our domain. So let's approach this the same way we did over here, which is think about what numbers are problematic for the original function and what numbers are problematic for the inverse function. Over here, I have f of x equals x plus 5. And where our eyeballs need to go is the denominator, x plus 5. What makes that 0? Well, x cannot equal negative 5. And that, if x equals negative 5, that's going to make the denominator of the original function 0, which means the original function is undefined. We use the same process to look at the inverse function. We're going to bring our eyeballs directly to the denominator and say, what makes the denominator 0? Well, it's going to be 3. And so the other part to our domain restriction is that x cannot equal 3, but this comes from the inverse function. Now let's write it out in our interval notation. All right. It's important that we line up those values from smallest to biggest. So we have from negative infinity to negative 5 in union with negative 5 to 3, in union with 3 to infinity. And all this means is all real numbers except x equals negative 5 and positive 3. Okay. All right, folks, that brings us to the end of the 3.8 video. Please let me know if you have any questions. I would be more than happy to clarify. All right, and I'll see you back here for the 3.1 video.